Yeah, yeah. Yeah, yeah, they also have the same demand. And they, sorry. Just a minute.
something like this. So there's a red rectangle. I hope you can see clearly. This is the mean, the red rectangle. Everything else is aligned. This is another example. So this is roughly how you should expect the aligned shape. Okay, we are just showing the results and then you can either keep on working on your code or so for these set of rectangles that we saw, the aligned set of rectangles will sort of look like this. Okay, so these are the generated rectangles. It's not visible in the mean. I've dotted it in black, but unfortunately it's not visible. All other generated rectangles have been aligned with the mean. That is, I hope, visible to all of you. Is this result interpretable? It's all rectangles aligned with the mean shape, which is also a rectangle. Yeah. I think right. No. Because all the rectangles are now size unit. That is why the endpoints sort of appear in that. But there is no magnification as such. Right. So those with very small aspect ratio and very high aspect ratio, they will sort of look like very thin or very fat rectangles. That depends on the aspect ratio. Is that okay? Okay, so the next important thing is the principal shape variations. So first principal shape variation, can you explain that to me? How would you interpret this? So the black rectangle, I don't know if it is visible to you guys or not. Somewhere exactly in the middle. We see, right? Yeah, yeah. This one. That's your mean shape, mean rectangle. Then, as we saw in the slide, all I'm talking is mean plus 0.1 times the first eigenvector, point plus 0.2 times the second eigenvector, plus 0.3 times the first eigenvector, minus 0.1 times the first eigenvector, so on and so forth. That's the 7 rectangles that you can see. So what is the interpretation of this? Sorry? Oh, need a proper interpretation. That is fine. But looking at this result, give me an interpretation in terms of what is changing in the rectangle. How to interpret this variation? Picture is okay, but finally, how should a human being interpret this? What is changing? Sorry? Translation. This translation, I mean, all these rectangles have their mean at origin. No. The answer lies in the code that is used to generate the rectangles. Aspect ratio. That is what you have changed, right? So, of course, the first major variation you expect is change in aspect ratio, right? Rectangles becoming thinner or fatter. Just change in aspect ratio. Okay? One who interprets the second direction of variation will get maybe a bar of chocolate or whatever, as far as it is available on campus. This one. Think about what you're answering. Angle. Where is there any change in angle? All of them are oriented in the same way. Scaling. So, do you expect that variation? We spend the first 1.5 hours talking about removing scaling, translation, and rotation. Now you are saying the second most major shape variation is scaling. Does that make sense? It's not a very trivial answer saying it's not quite completely away from your reach as well. Why should this appear? Yeah, I'll give you 5 minutes. Think about it. Once again, one who answers it correctly will get a bar of chocolate, whatever you want. Sorry. Yeah. Yes.
What does that mean?
So if you remember the slides, there's a mean car and then there were principal directions of variations and then mean plus 1 step along the direction, 2 steps along the direction. So that is what it's. So that's mean plus principal, mean plus 1 step towards principal direction, 2 step, that's this figure. It says mean plus the second principal variation. So there is nothing wrong in the code. Hopefully you will be able to reproduce this. Yeah, it's scaling, right? I mean, you can see.
There are many models.
Do you expect that? And if not, why is it coming? Can you?
We saw that a shape where there is a kind of circle. So majority they were going in this direction. So the first variance is in this direction of the corner. But if you observe they slightly changing the direction while traveling to circle in this direction also. They are not completely like straight lines going away. If that variance, the second gets variance.
But they are only corners in the rectangle, right? Don't you?
Would be the direction of one corner. The direction in which the change that is yeah, this the largest business from
And there's only one distance, right? This distance will be by that.
no, what I'm saying is you have to recognize the distance from one edge to another edge would be less than the distance from one corner.
Okay.
So
But we are not even picturing the distance between edges at all, right? Every rectangle is represented only by the four vertices. These edges are just drawn for the purpose of visualization. Sorry. Shifting landmark points. No. Right. Right. No, that's right. But what seems to be visible from this is contradictory to our assumption, right? Size should not be there in a shape variation. Why is that coming? It's clearly scaling, right? And why is it showing up like this? The aspect ratio is not changing. Aspect ratio change is over here. While you are thinking about this, you also look at the third direction of variation and fourth. So what does that take us? It's no longer a rectangle. Remember, you also need to take a look at the lambdas associated with these directions. So what you see over here, these are the eigenvalues. So aspect ratio change the eigenvalue is 9.89. Scaling much smaller, but still it's 0.2, right? Then onwards, basically 0. Okay, so although eigenvectors you can compute, right? There's nobody stopping you from computing eigenvectors, but this eigenvalue tells us that in the set of rectangles here generated, there is absolutely no variation around third, fourth, etc., so on and so forth direction. So there's in principle no need to plot all the direction of shape variation starting with the third one. But the question still remains, right? You can plot it, of course. Yeah, yes. So yeah, these are the third and fourth. You can plot fifth, sixth, seventh, and eighth. In total, there are 8 directions of variations. Only first two are sort of slightly contributing more than anything else. Right? And in fact, you can see it's like 9.89 and 0.2. So you don't even know. Maybe 99% of the variation is basically aspect ratio. Right? But still a 1% contribution from scaling. So all these rectangles, before we compute the shape variations, scale all of them to unit size. Right? That is the reason why you see that. That is the exact reason why scale shows up as a direction of variation. Let me explain it. So all of these landmark sets are unit size. So therefore, all of these belong to surface of a hypersphere, right? So let's say this one is your mu. All these other few crosses represents rectangles that are aligned with mu. Okay? Now what do you do in PCA? Consider all these vectors. If they don't, I've not drawn them like vectors, but just assume these are vectors. And now, what do you do? Take this as your vector space and then find the principal direction of variation. If you do that, you see that first direction of variation typically be this. That is exactly the aspect ratio. What other orthogonal axis will be there? This one.
When I was explaining, I see there.
No. So each of these point is a rectangle.
Yeah, I said that they formed a rectangular line. They were those corner points of the even corners are
What I'm trying to say is this one point represents one entire rectangle. Right? So, in other words, the ECA does not take into consideration that these points are all lying on the unit circle. We think of this as a vector space centered or its origin is new. This is why you see this as the second direction of variation towards the origin. So scaling. Right? What is this direction towards the origin? It's nothing but scaling. Starting from this point on the circle, how do you go towards the origin? By scaling.
see that the for variance is just for the corners, right?
Yeah, yes.
So if I say that the corner, if you take one particular corner and it is moving, every variance towards in this direction.
But that's not the direction, right? We could be meaning by so all those rectangles that were aligned were unit size.
Yeah.
So
If you take one of the corners of the rectangles, you will see they were in one of the quadrant of the circle.
okay,
So if you consider that one circle and that one.
but that is you're talking about one vertex.
Yep, we are thinking of that in the one vector space, but if we consider one, that's the reason right of the circle, not the circle, variance graph, variance. It says the corners were going in the upward direction. Scaling. The second variance
Second, yes.
is going outward direction.
Okay.
For that corresponding corners, they were variance of in that direction. And
No. Right. So how do you get rid of this? Because see, problem is this is due to the curvature of the space, not due to shape. And it's the inherent or implicit variation that comes up because you are working or you have decided to work in unit size landmark sets. So this direction is not really giving you anything. Okay, so one easy way out is sort of project this way. This one is and then go easy on this.
if you have nearly infinite amount of sample, after the two variance, all the should be go to 7.
So how have you generated the rectangles?
The infinite randomly.
Right, but the only difference is aspect ratio, isn't it? So by generating more samples, you're not going to be able to produce anything else. It'll just be more number of points here.
Yeah, but then again, after the first, all the others derived.
Right,
Because I see that they wanted to
right. So for this example, they will be only two. But so it's the promise of the example. Okay, thank you. Yeah, so the first image is basically 41 landmark points per jawline. There are 300 such jawlines that I have just plotted as raw data. That's the first image. Second, hopefully it is there, you will be able to see a dark black outline. That's the mean jawline. That's how a mean human jawline should appear. And everything else is basically aligned with that image. Okay. Yes.
What about those data points must go on the string?
Yes.
Why so?
Because if you look at the images from which the jawline has been extracted, the direction in which the face looks at is not necessarily straight. So if I look sideways and then take my picture and then sort of try to capture my jawline, it will be sort of. Okay, let me see why it's not moving. Fortunately, I think I've used X and Y everywhere.
There's a function argument from my shape where it's good argument.
Oh, right. Okay.
Number 5 was
Changed it at the last point.
you know, you can do cell run on.
Let me see shape where
Or you can just do cell run on.
cell.
Run on. I think some error or something.
Yeah, I couldn't read this. And these properties. 4 comma. This was exactly what I was talking about.
You
4 should be 4 comma 1, I think. Let me just try this.
if you
Yes.
it's not minus number being what x not, it would not work out. Automatically does broadcasting.
Help me out. X0.
It's not minus. It's not minus. Now if I mean.
Right? Let's see.
think the same problem will be there. Anyways, I think you know, but dimension. Because I want to multiply the scale to every coordinate.
In this. Yeah, remove the number ones and we are to one.
Again, the same issue. P1, 4. Anyways, I think you can try out the data set is available. So as I remember, the first major direction of variation was a thin face to a pattern face. Okay, so the data set is available. We to try this out. If you are interested, I think I had written notes on whatever rubbish we did in the morning. I will share them on the drive in case you are interested. You can read them. Okay. It also talks about this particular thing complete. So here you have to figure out by what amount you should scale this. Of course, a simple calculation, but talks about that. I'll share that with you guys. Yes. Thank you. Hope to see you guys tomorrow.